Great. Okay, thank you very much to the organizers for inviting me to speak. I'm very excited to tell you about some work that hopefully will appear shortly in collaboration with Daniel Baumann, Kurt Hinterbickler, Austin Joyce, Hayden Lee, who is in the audience, Jaji May, and Nathan Murrens. Nathan was here, but I think he's on his way back to Amsterdam. Okay, so to set the scene for this, because it's going to be some things that maybe you haven't thought about so much, let's remind ourselves of something you probably saw in the quantum field theory class at some point, which is the sort of theoretical argument for why we don't expect to see massless spin-3 particles in nature. So the problem isn't that you can't write down interactions for these things. In fact, it's pretty trivial to do so. If you want to write down the interaction between a massless spin-3 and some scalar particles, the answer is basically some unique form that's something like the triple copy of the scalar QED vertex. If you take two of these vertices, you can sort of glue them together and form interesting observables. For example, you can glue two of the gauge lines together and then expand in the limit of small momentum transfer to calculate a potential. And if you do this, you'll find that you get an answer that falls off like 1 over r to the d minus 3. So in d equals 4, this is 1 over r, like Coulomb's law or Newton's law. And this is what we call a long-range force. So if these things existed in nature, we might expect to see them in the LHC or in solar system tests or all over the place. The problem is that once you have this vertex, you can glue it together in a different way, where you glue together two of the matter lines. And now you have something that's more like Compton scattering. And of course, this is, in general, a very complicated object that involves contact terms and so on. But there's a nice simplification if you expand this thing in the soft limit of one of these gauge particles. Then all those contact terms go away, and you just get something that depends on this on-shell 3-point vertex. If you take that soft expanded Compton amplitude and plug in a longitudinal polarization for the gauge boson, you get some kind of combination of 3-point amplitudes that has to sum to 0. And actually, Steve Weinberg, long ago, explained that if you study this expression in generic kinematics, there's just no way that it can be 0 unless you set this overall coupling little g to 0. And therefore, we don't expect to see these long-range forces in nature because this coupling is just inconsistent. So this is a very famous argument. And today, the point of this talk is that I'm going to explain how to replicate this style of argument and these kind of constraints in de Sitter space. So this talk is not mostly going to be about bulk de Sitter, but just to remind you, here's a picture of the Penrose diagram. There's a spatial boundary in future infinity, which in these Poincare patch coordinates corresponds to eta going to 0. So that's like the infinite future. If you want to think about this as inflation, this is like the end of inflation. So to construct some kind of Weinberg-like argument for objects in de Sitter, we want something like a scattering amplitude. And I'm going to claim that the most natural object of this kind is what's called the Bunch-Davies wave function. So formally, this is defined as some path integral over whatever bulk fields you have with some boundary conditions. There's a boundary condition in the infinite past that projects onto positive frequency modes that defines this Bunch-Davies vacuum state. And then the fields also approach some specified boundary values at this future boundary with some scaling dimension delta, which is defined as some root of some polynomial equation, which may look familiar if you studied ADS-CFT, except that there's a crucial minus sign difference, which comes from changing from anti-de Sitter to de Sitter. And the reason why this is a nice object to study is it has all of the same kinematic properties as the generating functional of correlation functions in a Euclidean CFT. So that means that we can open our favorite review on CFT and start using that sort of standard results to say something about this Bunch-Davies wave function. So this is, in a sense, a very weak version of the idea of the DS-CFT correspondence that Strominger proposed a long time ago, but we're not actually requiring that there exists a truly dual theory to whatever lives in de Sitter. We're just using the sort of tautological fact that it's going to have the same kinematic properties as a CFT. Okay, so this lets us import standard technology to do things like bootstrap on-shell interactions. For example, if we want to count how many 3-point interactions there are among gauge fields in de Sitter, this can be mapped onto some problem on the boundary of constructing conformally invariant correlation functions of conserved currents. And indeed, you find that there's two such structures. This is so-called embedding space notation. It's not really important that you know what it is. But the answer is that there's two such structures, and these map directly onto Yang-Mills and F cubed. The same sort of problems we deal with in flat space. Okay, so the starting point for some systematic exploration of these de Sitter amplitude-like objects is to enumerate the kind of free field theories that we can have. And Wigner explained long ago that these are one-to-one with the unitary irreducible representations of the isometry group. So it's worth thinking about why this is different between de Sitter and anti-de Sitter, since the symmetry groups are sort of formally related. They're both versions of the conformal group. In anti-de Sitter, if you start with Lorentzian ADS, then the boundary correlation functions are reflection positive. This is the sort of normal notion of unitarity in a CFT. But in de Sitter, there's a very different notion of unitarity because of the different spacetime signals. So in de Sitter, the unitarity condition is that p dagger goes to p and k dagger goes to k. And so the classification of the irreps is different. But this was solved long ago in the mathematics literature. So today I'm going to be talking mostly about these symmetric traceless spin S tensor fields. And the representations come in three different types: the so-called principal and complementary series, which are just sort of ordinary massive symmetric tensor fields, and then the so-called exceptional series, which is a discrete set of representations, which is just a fancy way of saying the gauge fields. So unlike in flat space, the exceptional series representations are labeled by their spins, but also by an additional discrete parameter called the depth. The depth is some integer that goes between 0 and s minus 1. When the depth is s minus 1, which is maximal depth, these are just ordinary massless gauge fields. But in de Sitter, we also have these exotic gauge field type objects, which have less than maximal depth, which are called partially massless gauge fields, and they just have no analog in flat or anti-de Sitter space. So the main problem that has actually been going on for decades, but I'm going to try and make some progress on in this talk, is to determine if there are consistently interacting theories for these partially massless representations. So it's a little bit more intuitive to draw a picture like this, where you have spins on the vertical and masses on the horizontal. The statement of these exceptional series representations is that there's a critical line called the Higuchi bound, and if you're to the right of this, then you have a continuum of massive representations, but if you're to the left, you only have a discrete set of representations that you're allowed to have. So in particular, this means that in de Sitter space, you can't have an arbitrarily light massive spin 2 particle. You can be either exactly massless like the graviton, or you have to make a discrete jump to a finite amount of mass, and then you're allowed to be generically massive. So in terms of the field theory, the way to understand these partially massless fields is to start with the free field equations for a generic massive spin 2, for example. And the claim is that if you tune the mass parameter to some critical value, which defines this Higuchi bound, then this field develops a scalar gauge symmetry. A scalar meaning that the gauge parameter here is a scalar. So 1 degree of freedom is decoupling. So that means that in 4 dimensions, where a massive spin 2 normally has 5 polarizations, when you tune it to this critical mass value, one of them decouples, and you end up with some exotic object that only has 4 degrees of freedom. Okay, but we don't want to do bulk field theory. We want to do this sort of boundary amplitude-like on-shell construction. So we need to know what these things correspond to in this boundary CFT. And this was actually explained long ago by Dolan, Nappy, and Witten, relatively early on in the ADS CFT literature, that these partially massless gauge fields in the bulk would be dual to some conserved current on the boundary, some primary of spin S, which has some sort of exotic partially conserved current conservation condition. So a normal conserved current is something that is annihilated by taking one divergence, but actually these partially massless fields, if they have non-maximal depth, are annihilated by taking S minus T divergences. So I'll use this notation throughout this talk, which is this X sub S comma T. So S is the spin and T is the depth. So an X sub 1 comma 0 is like an ordinary conserved current of spin 1. So this would be dual to a photon in the bulk. An X sub 2 comma 1 is spin 2 depth 1. So this is an ordinary conserved spin 2 operator, which would be the stress tensor, which would be dual to a graviton. And then the first interesting thing is this partially massless spin 2, which is a 2 comma 0, which is annihilated by taking divergences on both of its indices. Okay, so our strategy is going to be to try and derive bounds using a strategy that was used in this paper by Maldacen and Zhiboyedov around 15 years ago. So the idea is that once you have these boundary conserved current operators, you can define a topological surface or charge operator. So the idea is that you take S minus T minus 1 divergences of your current. And so you get some object that if you take one more divergence, you get 0. And then you just construct an ordinary topological surface operator by doing a surface integral. If you insert this thing into a correlation function, on a surface that links all the local operator insertions, then you can evaluate it in two ways. One is you can shrink it down so that it wraps all of the individual operators and acts on them locally. Or you can imagine closing it on the other side of the sphere, in which case you're measuring the charge of the vacuum. And my assumption is going to be that the charge of the vacuum is zero. So in the bulk, this corresponds to the assumption that these gauge fields are in their Coulomb-like phase and not in a Higgs phase. Okay, so this gives you some interesting kind of sum over correlation functions that has to be zero. And a priori, we don't know the way the charges are supposed to act on the individual local operators, but we know that it's some combination of primaries and descendants in the theory with some a priori unknown coefficients. These coefficients are related to the OPE coefficients, which are the three-point functions of the theory. And so this turns out to be very interesting if you write down this constraint for the insertion of this charge operator in a three-point function, then you get some kind of sum rule that just looks like a bunch of conformally invariant three-point functions being acted on with some differential operators with some unknown coefficients. So the coefficients appear both here and inside of the three-point functions, and so this gives you some sort of quadratic constraint on the three-point couplings of the theory, and it just has to be true for any consistent theory of gauge fields in de Sitter. Okay, so that was a bit formal. Maybe I can explain this with an example that's a little bit clearer. So the simplest example is one of these spin 1 depth 0 current operators. And I'm going to assume it couples to some scalar fields, O1, 2, 3. And we don't know how the charge acts on the local operator, but actually, if you think about it, there's only one way it could act that's consistent with matching scaling dimensions on both sides, which is to multiply the operator by a number. And so if you write down this sum rule, you get some identity which says that the sum of these numbers, Q1, 2, 3, times the three-point function has to be zero. And so there's only two options. Either the sum of these Qs are zero or the coupling is zero. And in the bulk, we've just rediscovered electric charge conservation. So if we do the same thing for this x2, 1, this massless spin 2 field, then again, the operator, which now has mass dimension 1, can only act on the local operator in one way. It can act with a derivative because we have to match the number of Lorentz indices. Again, we get a sum rule, and the only way that this sum rule can be true is if you set all the kappas to be equal, in which case you discover that whatever the dual field is coupling to everything with universal strength, and this is the Einstein equivalence principle. So I hope these examples sort of hit you over the head with the fact that these just literally are the Weinberg soft constraints for the familiar cases that we know. Okay, so now we understand how this works. Let's do some unfamiliar examples. So the simplest thing we can do is we can think about one of these partially massless fields coupled to some scalar field. And we're going to try and build something that's like electrodynamics. So we're going to assume that this partially massless field doesn't have a self-interaction. In that sense, it's like an abelian gauge theory. And so the simplest thing is, say, spin 3 and depth 0. The charge operator has mass dimension 2. And so you want to write down some way that this thing can act on local operators that's consistent with the scaling dimensions. And so the only thing you can write down is that you get back the local operator acted on with a Laplacian. And so you write down again your sum rule. And it turns out to be just a normal three-point function. This is some unique thing. There's only one tensor structure for a spinning field and two scalar fields, acted on by some differential operator, which is box 2 minus box 3. And you can just check and convince yourself that this is not zero unless you set this overall coupling C to 0, in which case the model is ruled out. Just exactly the same logic as Weinberg's argument. Okay, let's do it again for spin 2. Here it's a little bit tricky because the charge operator has mass dimension 1. So the differential operator that would appear on the right-hand side would want to be something like Laplacian to the 1/2, but that's not a local operator. It's actually telling you that the minimal coupling for one of these spin 2 depth 0 objects actually couples to two different operators of different mass dimensions split by 1 unit. And so this is the only consistent way that it can act on local operators. So then you write down the sum rule. Again, you get a sum of two things, and the only way to make it 0 is to set the overall coupling to 0. So this thing's also ruled out. It's actually pretty straightforward to generalize this to all different cases, models of this partially massless electrodynamics type. So for example, for S even and T odd, you get some identity that looks like this. And in all cases, the only way to make this satisfied is to set the coupling to 0. And so there's a no-go theorem for models of partially massless electrodynamics that generalizes previous things that had been discussed before. Okay, but that was an ad hoc construction. I just sort of assumed a kind of interaction in the theory. We want to do something more systematic, and the way to do that is to think about coupling these things to gravity. And the reason this is powerful is that gravity couples to everything universally. So there are some interactions in the theory that you're not allowed to set to 0. In particular, the graviton couples to matter fields and to itself with the same strength that in the bulk is determined by the square root of g Newton. And in the CFT, this corresponds to the way that the charges that you build out of the stress tensor act on local operators. And it turns out that you can show if the charge operator has spin greater than 1, sorry, if the underlying current operator has spin greater than 1, then it implies that the current algebra, which is the way the charge acts on the stress tensor and the way the charge acts on itself, are related to each other in such a way that they have to form some larger algebraic structure called a higher spin algebra. So in other words, as soon as you have a partially massless gauge symmetry and a stress tensor in the theory, you now have some larger algebraic structure that you need to satisfy, and this is very constraining. Okay, so our strategy is to use this fact that there are some non-optional interactions in the theory to write down some sum rules that can't trivially vanish. So the first is what I call the Mueller scattering constraint, which is sort of like a 4-point function where you have 4 of these x's on the outside. And there's a non-trivial contribution that comes from exchange of the stress tensor. So for this to sum to 0, it has to be canceling against something else in this sum. There's a second non-trivial constraint, which looks like Compton scattering, where I have 2 stress tensors on the outside. And again, there's some non-zero contributions that have to cancel against something for this to give you a consistent result. So we proceed in a sort of algorithmic way. We're going to assume that we have an initial spectrum of operators, which consists of, say, the stress tensor and one of these partially massless fields. Then we're going to write down the most general possible current algebra that we can. So this will be like the charge acting on the stress tensor, the charge acting on the partially massless field. We'll construct the most generally conformally invariant 3-point functions that we can. Both of these steps have finitely many unknown parameters in them. Then we write down these charge conservation constraints, and we try and solve them simultaneously in generic kinematics. If there's no solution, then a model with the assumed spectrum is rigorously ruled out, and then you can try and enlarge the initial spectrum by adding more operators and starting again at step 1. But actually, there's only finitely many things you can add consistently to the current algebra, and so there's only finitely many ways you can possibly save yourself. So this algorithm can terminate, and you just rule out the theory completely. Okay, so the simplest non-trivial example of this type is a graviton coupled to one of these partially massless spin 2 fields. And so I claim this is the most general form of the current algebra. So it consists of a bunch of new fields which I've added, which is this massive spin 2 and then 2 partially massless spin 3s, and there's nothing else that you can consistently add. And so we analyze the constraints that you get from this in dimensions 3 through 7, and I'll just qualitatively tell you what the results are. So it's pretty straightforward to show that you can never possibly have a consistent solution if you just have the minimal spectrum of just the partially massless field and the graviton. So minimal here is like minimal supergravity, where you just have the graviton and the gravitino. So you need to add other things to be consistent. In d equals to 3, you can find a consistent solution where you have the minimal spectrum plus any 2 of the additional fields. And in dimensions greater than or equal to 4, you can find a consistent theory that just has the massive spin 2 in addition. So d equals 3 is the physical dimension. D is the number of boundary dimensions, so it's 4 dimensions in the bulk. So in principle, this is a phenomenological prediction. It says that during inflation, if you see a very light massive spin 2 particle that's down near the Higuchi bound, you're going to have to see at least 2 out of 3 of these other excitations with these specific masses. So maybe. Okay, the next simplest case that you can consider is a graviton with a partially massless spin 3 of depth 0. Here, the current algebra, again, is finite, but it's a bit more complicated. You can consider adding operators all the way up to spin 5 consistently in this case. And again, we analyze the constraints in dimensions 3 through 7. There's no minimal theory. And in dimensions greater than or equal to 4, there is a consistent solution where you add 2 of these additional fields. One is a massive spin 2, and the other is a partially massless spin 4. Okay, so you might worry. So what I've done here is I've just analyzed the simplest set of constraints, but to find consistent solutions, I've had to add new things. So that means I should go back to step 1 of my algorithm, and I should do it again, because now I have more things that are also gauge fields, so they have their own set of constraints. And you might worry that if I keep iterating this thing, I'm eventually going to rule out all of the models, because the constraints could feed back down. So how do we know that these remain consistent solutions when we add more constraints? And the reason we know this is because there's another way of approaching this problem, which is to just try and directly construct a CFT that satisfies these constraints, like all of them. And so that sounds very hard. How would you write down a CFT with these exotic operators? It's actually very easy. So there's a whole zoo of non-unitary free CFTs that you can write down, which are generalizations of the usual vector models. So the idea is that you just take a set of, for example, n complex scalar fields, and you replace the kinetic term with something like box to the k, where k is some other integer. You can do the same with the fermions, where you replace the kinetic term like this. And it's very easy to show that these are conformal field theories. They're completely free, so it's trivial to do that. It's also trivial to compute any correlation function you want. And you can see that they have certain symmetries. And if you compute the Noether currents associated with these symmetries, they are genuinely these partially conserved current operators that we've been studying. And so the simplest example of a model of this type was studied in detail by my collaborator, Kurt, a couple of years ago. It's this so-called box squared CFT, which is k equals 2 in the bosonic case. And if you work out the spectrum of primary operators, you get two sort of infinite towers or Regge trajectories. One which has a sort of infinite tower of massless fields, including the stress tensor, and then a second infinite tower that contains an infinite set of partially massless fields of lowest depth is the 3, 0 here. And so these should give a consistent solution to our constraints in dimensions, well, for technical reasons, dimensions 5 and 7 and above. And indeed, we were able to confirm this, and is a check that what we're doing is self-consistent. In d equals to 3, this model actually doesn't exist because it contains in its spectrum an operator that's neither a primary nor a descendant. But this gives a sort of doubly infinite family of consistent solutions to our constraints in general. Okay, so for k equals 1, which is the usual unitary case, these have been studied. This is the famous GKPY duality between the large n limit of these vector models. And the claim there is that in anti-de Sitter space, these CFTs are dual to some Vasiliev-like theory in the bulk. And there's two unitary theories on the boundary, and these correspond exactly to the two different versions of Vasiliev theory you can have in ADS. And as a consequence of this famous classification theorem of Maldacen and Zhiboyedov that showed that these are the only consistent CFTs with highest spin conserved currents, we actually know that these are the only consistent highest spin theories in ADS. And so the $1,000,001 question is, are the bulk duals of the non-unitary theories, these free theories with k greater than 1, the only consistent partially massless theories in de Sitter? So our results do not show that this is the only solutions, but the idea would be that if you iterated this algorithm far enough, you'll eventually converge down to the spectrum of one of these two theories, and you'll reproduce them. So it's an open question whether there are more things beyond this. Okay, so these no-go theorems that I've been presenting are only as strong as their assumptions. And so implicitly, the assumption I've been making, well, not implicitly, explicitly, the assumption I've been making is that the gauge field in the bulk is dual to some conserved current operator on the boundary. And so it turns out that this is actually, well, there's an additional subtlety here. And it's relatively easy to construct examples of gauge invariant interactions in the bulk which don't correspond to conserved correlation functions on the boundary. So the simplest example is a partially massless spin 2 coupled to two scalar matter fields. So what you can do is you can take a linearized gauge transformation of this bulk vertex and ask for which values of the conformal dimension is this thing gauge invariant. And you get two answers. Either the scaling dimensions of the operators are differ by 1, which is the answer we got in this partially massless electrodynamics example a moment ago, or there's a second answer where one of the dimensions is replaced with its shadow. And in fact, both of these correspond to gauge invariant bulk vertices. But if you take the second solution and you actually compute the 3-point Witten diagram and then take the double divergence, you don't get 0. What happens is you get an answer that has a vanishing prefactor times an integral, which turns out to diverge at exactly that value of the scaling dimension. This is a so-called extremal correlator. So what this is telling you actually is that the boundary conditions that you've assumed have actually broken the bulk gauge invariant, and they've broken it by a so-called double trace deformation. So this means that the gauge symmetry in the bulk is being Higgsed. So there are certain gauge invariant interactions in the bulk that are just incompatible with the boundary conditions we're assuming. And this subtlety turns out to be important to understand a model called conformal gravity that I know a number of amplitudes people are interested in. And so the claim here is that, and this has been known for a long time, that if you take conformal gravity and you expand it around a de Sitter background, then you'll see that the spectrum of fluctuations consists of an ordinary massless spin 2, like an ordinary graviton, plus some additional degrees of freedom which organize in de Sitter into one of these partially massless spin 2s. And this is a manifestly consistent theory in de Sitter. It's not unitary, but it's manifestly gauge invariant. And so this should have been a consistent solution to our constraints, but we didn't find it. And the answer is because of this problem with boundary conditions. It turns out that the gauge symmetry of this partially massless spin 2 is actually broken by one of these double trace deformations. And what that means is that actually this partially massless spin 2 thing isn't actually partially massless. It gets a mass at one loop. So there's an anomalous dimension that the operator gains at subleading order in 1/n. And so it's consistent that we didn't find this as a solution, but it suggests that there's a sort of extension of this program where you start thinking about all of the different ways that you can break these symmetries by double trace deformations, or which is equivalent to the statement of all the different ways that you can Higgs the gauge symmetries in the bulk. Okay, but that brings me to the end of this talk. So I'm just going to conclude with this picture. So the basic problem that we were studying was to find to classify and find the consistent gauge theories in maximally symmetric spacetimes. And as in all things, de Sitter is the least understood of all the maximally symmetric spacetimes. Most people in this room study scattering of gauge theories in Minkowski space, where we understand things extremely well. And we understand the classification of gauge theories in both flat space and anti-de Sitter space. But in de Sitter, there are still open problems. But I hope I've convinced you that there is a systematic way to attack this problem, and we're starting to make real progress. Okay, thank you very much.